So welcome back to today's video. In today's video, I'm going to take a look at doing just a couple of the exercises from Lab 4, and then I'm going to build on those exercises so that I can complete the exercises in Lab 5. So the first thing I needed to do was make a couple of changes to that account.cpp. That's the one which we used in Lab a couple of weeks ago. So I just grabbed a copy of it. I included a string. When I'm accessing a string, I'm getting that from the std namespace as well. And then I amended my constructor so that it can take in that string name. I made a set name and a get name function, and I've also overloaded that cout operator. So now I need to create a node, and it's going to be a doubly linked node. Just to explain, you've probably heard this before, but that means my node is going to have a pointer which goes to the next node along in the list, and it's going to have a pointer which is going to the previous node in the list. When nodes are initialized, it's probably a good idea to have them set to null, and then you can just move them around as you need. You can also overload the constructor so that we can set them up to link to actual nodes. The other function of a node is to store a data type, and in our case the data type is going to be an account. In the end, essentially what you'll end up with is like a list of nodes, and we'll use the linked list class to manage this list. But the nodes themselves are literally just, it's a node entity, it's got a pointer going to its next node, and it's got a pointer going to its previous node. If you're at the head or the tail, you're going to be pointing to null in some cases. So your previous node at the head will go to null, and your next node at the tail will go to null. Of course, it's different if you're in a circularly linked list. They will just link round to each other. The head and tail will link to each other. But in this one, we're just having a standard linear linked list. So just taking a look at my node class, I start off with my private member variables. That's my data type, which is here. That's actually coming from my type def, which is an account. Remember, we're including an account. That's going to be our data type. I've used type def much like what we did last week so that it just flows through the solution and it's easy to update my node class for other data types. So that's my data there. Next, I've got my node pointer, which is going to my next node, and it's also got another one going to my previous node. One of the things I've had to do here is I've included the C standard library, and that's because that's going to give me access to this null pointer. So that way, if I initialize a node and I don't set pointers for it at initialization, it will set those to null. The final thing you might notice about my .h class is that I've included the implementation of the functions inside it. It's perfectly legal in C++ to include your implementation here in the .h file. And on a really small class like this, it's okay to just have your implementation of the functions here. You wouldn't do it on a bigger class that's going to have more algorithms and things within them. So finally, you'll notice that I've actually overloaded my getPrevious and getNext node pointer functions. The reason why I've done this is so that I can work with both const nodes and regular nodes. So if I've got a regular node and it's just trying to get the next, it will automatically go and use the implementation that it needs. If I've got a const node here, and this one's going to use getNext, it will go and get this one and run with that one. Essentially, the implementation's all pretty much the same. You just need to make sure that you do include both. So now that I've got some of those data structures set up from Lab 4, I can move on to the Lab 5 exercises and get started on my linked list. Let's just say a linked list is going to be the data structure which is responsible for creating and maintaining those nodes. So it's going to create the node, it's going to make sure the node has the right data type associated with it, and then it's going to keep track of this list through the use of a head pointer and a tail pointer. In the case where you only have one node, you're going to have a setup similar to this. This is where the head pointer and the tail pointer are both pointing directly at the same node. However, in the case where you've got a proper list set up, so more than one node, you're going to end up with a structure that looks similar to this. And this is where you've got your head pointer pointing at a head node, and your tail pointer is, surprise, surprise, pointing at a tail node. And then the rest of the list structure, the internal list structure, is going to be maintained by that node's own property, which is obviously the next pointer or the previous pointer. Because we're doing a linear linked list at the moment, this means that your node previous for your head node is going to point towards null, and likewise your next node at your tail pointer is also going to point towards null. So the first thing to note about my .h file is that I'm including the node.h because obviously the linked list is responsible for creating nodes. I'm also including account.h, and that's because this is my account type. It's the data type, and my nodes data type and linked list data type, they need to match. Pretty obvious why. If your linked list is creating nodes and somebody passes it an object to add to that node, then you need to be able to pass that through. And then down here you can see I've got my head pointer and my tail pointer. So I'm first just going to have a very quick look at the constructors I've made for this linked list. I've got one where you can construct an empty list, and I've also got one where you can construct a list that's going to include its first node. So if we look at the implementation here, you can see this one is constructing an empty list. All I have to do is set that head pointer and tail pointer to null and the list length to 0. In the case of actually having a data item ready to make and create with that node, all I have to do is create a new node, and I'm creating it on the heap. My head pointer here has already been declared. So if I look here, I've already declared that that's going to be a pointer towards a node. So all I have to do is say head pointer, whoopsie, down here. All I have to do is say that my head pointer is going to the new node, which is going to be on that heap. And the node is being created with that data type. Then I'm going to set that tail pointer to that head pointer just to make sure, so just to show you, I'm just creating this situation here. And then I'm going to set the list length to 1. So now I'm going to take a look at how to add nodes to the head and the tail of the list. To do this, it's fairly simple. First, you have to take into account the case of the empty linked list. And this is the same as what we did in our constructor. It's just wrapped in an if condition. So if the list is empty, then we're going to set up our first node. And that's just going to look like this, exactly the same as what it was for the constructor. For any other time when you're adding a node, the first one we're going to look at is adding to the head. You want to follow a very simple process. You can see here it's really quite small. What it looks like is you're going to create that node. You can assume the data type is still attached to it. I've just taken it out of the presentation because it runs a little easier, looks a bit neater without it. But essentially we're going to be creating a new node, and we're going to be doing that with a pointer. This pointer is temporary, so we're going to keep it around for here just so that we can keep access to that node while we're tidying everything up. When we create this node, what I'm doing, I'm invoking the constructor where these guys are going to be set to null. So you can see his next pointer goes to null, his previous pointer goes to null. I'm then going to manually adjust it so that the pointers are moved around. And then finally, I'm going to move that head pointer to the new head of the list. You can see this is my code here for doing that. So all of my pointer maintenance is in these 3 lines here. The very first thing I do is I go to the node at the head pointer and I set its previous pointer to the node I've just created. So that's that step there. The next thing I do is I go to my head insert, so I go to this node here, and then I set its next pointer to the current head. Finally, I move the linked list head pointer along to the node I just created. That's that line of code there. I increment the list length because that's normal, but then what I want to do is I want to get rid of this pointer because I don't need it anymore. The thing I have to watch out for is that I don't use delete at this time. If I was to say delete head insert, what that would do, that would actually get rid of my node, and you can see the list would be pretty broken. So instead what I do is I just say set that guy to null, and then that just tidies everything up, and that leaves my linked list in this state. As you can imagine, adding a node to the tail of your list is generally exactly the same. It's just basically the reflection. So you want to take care of that case for your empty list, but then otherwise what you're going to do is you're going to create a new node, and that's going to be called tail insert. Then that's going to be created with the null pointers. Then what you want to do is make sure you move these around correctly. So you want to take the current tail and you want to move that guy to the new guy you just created. Then you want to take the new guy you just created and set his previous to the current tail. Finally, you want to move your tail pointer along the linked list tail pointer. Then you're just going to increment the length of your list and get rid of that pointer, that new pointer. So that's the way you would go around inserting at the tail. So I'm going to now take a look at removing nodes, and I'm going to remove from the head and remove from the tail. You'll notice in this lab sheet they've asked you to return the value type for the node that's being removed. I've decided to implement mine as a void function. So you'll see here, this is my remove from tail, and I'm not returning anything. The reason why I'm doing that is because I'm going to incorporate a bit of memory management, and I'm actually going to delete that node that's being removed to make sure that the memory on the heap is released. So removing a node is actually easier than inserting it. In the case where I'm removing from a head, the process is really simple. So let's say I'm dealing with the case where there are actual nodes in my list and there's more than one. All I have to do first is set up a new temp head pointer, and that's going to point at that original head node there, the guy that I'm trying to remove. Then I just need to move the head pointer along to the next node in the list. So that's me moving him along to the next node. There we go. And then all I need to do is delete this. I want to take this guy off the heap, release that memory. So I'm just going to delete the node at that place, and then I'm just going to decrement my list and get rid of that pointer. So you can see everything tidies up pretty easily. It's a fairly simple process for doing it. Doing it for the tail is essentially the same. Make a tail temp pointer, move the original tail pointer, like the actual tail pointer, along, delete the node. You'll notice that I don't need to do any pointer management. That should all just take care of itself. The only thing I have to do is set this guy to null. Oops. And then I'll end up in that state. There is a condition where you do need to handle this case differently if your list length is 1. So if you've got the last node in the list, you'll handle it the same for both removing from the head and tail. Essentially, all you do is delete this node, get rid of the pointers, just set them to null, decrement the list length so that it's accurate, and that's it. That's literally all you have to do. The final thing is there's the case of if you're working with an empty list and somebody tries to remove a node. I'm just doing nothing. I'm literally not doing anything and just returning. I'm assuming that, you know, the programmer was a bit silly with what they've tried to do. What you could do is include an assertion here and say, well, you're trying to remove a node from an empty list, can't be done, and actually terminate the program. It's up to you how you want to implement that case there. Taking a really quick look at the destructor, what I want to do with my destructor is make sure that all of the items are removed. So I'm going to loop through until we get to the head pointer equaling null, and then I'm just going to remove those nodes from the head. So now we're going to look at introducing a current pointer, and that's going to be used to iterate over the list. We're going to be able to move that pointer around the list, and we're going to be using that to get the data type. We'll also just quickly look at the size t size function, since, I mean, it's tiny, but yeah, we'll just do it since it's here. So the idea of a current pointer is mainly so that we can keep track and use this to move around the list. We're always going to want our head pointer to point to the head of the list like this. We'll always want our tail pointer pointing to the tail of the list. But what we want is a current pointer that's going to be able to move forward, it's going to be able to move back, it's going to be able to jump to the head of the list if we need to. We can make it jump to the tail of the list. And we're going to be getting our data. So when we return the data type of a node, it's going to be done just using this getCurrent. So the implementation is actually really simple, just this part of the implementation. All I've had to do is include a current pointer. These are the functions forward, back, move to head, move to tail, get current, and size t. Just to show you down here, you've got the forward, it's just moving it along to the next one. You've got the previous, it's just moving it along to the previous one. Moving to the head is just getting that pointer to match the head pointer. Moving it to the tail is just matching the tail pointer. The current pointer getData is going to return that data type. And then obviously with the size, just to look at it, we're just returning the length of that list. When I'm initializing the current variable or the current pointer, what I've done is I've amended my constructor so that when I'm doing the empty list, it's going to be set to null. When I'm doing a list that has a node, I'm going to set that current pointer to that same node. And then I've also adjusted my add to head and add to tail so that that's going to account for that current pointer now when you're adding that first node. So when it comes to adding a node at our current pointer and removing the node which our current pointer is pointing at, I'm actually going to leave those for you to implement as just your own exercise, but I will just go over some of the things you'll need to consider when implementing these functions. So what's going to happen is, let's say we're in this situation where we've got some nodes and our current pointer happens to be at the tail. There's going to be a decision you'll need to make about whether you're going to insert nodes before the current pointer or after the current pointer. Generally, I think you'd insert them before, but we'll look at both situations. So in the situation where you're inserting a node before the current pointer, what you would do is you'd create that node, you'd make sure you've got a temporary pointer to it so you can access it. You can see when you're doing nodes that you're going to need a little bit more pointer maintenance when you're working with the current node, and that's because you're going to have 2 pointers to set that way, and you're going to have 2 pointers to set that way as well. So in total, you'll need to move around 4 pointers. Then you'll need to make a decision about whether your current pointer is going to stay at the node it was currently at, or if it's actually going to move over to this node here. It doesn't really matter which one you choose, you just need to make sure you document it and choose one, and if you're told which one to do, then do whatever you're told to do in any linked list. The other option when you're in this situation might be that you're adding nodes after that current node. Now, if you're doing that, it's going to, because we're at the tail already, you're going to end up in this kind of situation where you're going to create a node, you're going to play around with the pointers. There's a little less pointer maintenance in this one because that guy's still going to go to null. And then what you're going to need to do is make sure you're moving that tail pointer along as well. So that's your edge condition for making sure you need to realign that tail pointer. So just to go over exactly what you need to think about, just how are you going to insert at the current pointer? Are you going to insert the nodes before the current node or after the current node? Then once you know what you're doing, you just need to work out which boundary conditions you're going to deal with. And is that going to be dealing with the boundary at your head pointer or dealing with the boundary at your tail pointer? And the final thing you need to do before, like, just answer to yourself is how are you going to maintain that current pointer? So is it going to point to the new node, or is it going to maintain its current position? Once you know how you're doing that, you're free to go ahead and implement that function. When it comes to removing nodes at the current pointer, that's actually shouldn't be too tricky, but I'm going to leave that entirely for you guys to sit down and think about. So the last thing we need to do is just write a program that's going to demonstrate the features that we've just made in our linked list. I've just got something tiny to get started with. All I've got is a main.cpp again, and I'm including the linked list, and I'm including the data type account. And that's because I'm going to create accounts and then I'm going to push them into that linked list. All I do is create a new linked list straight up. Then I'm just adding new accounts, but I'm doing it in a for loop. You can see here I'm adding accounts on the heap, and then I'm adding it to that linked list that I've just created. So that's it, going onto the linked list. The account should be changing in value, so it should be going from 0 through to 90. Then I'm just going to print out those details of the account. Again, I'm using the current pointer to do that. So I've moved the current pointer to the head, and then I've just pushed it along through the list. So at the end of each loop, I'm just moving it forward by 1. And all I'm doing is a cout, and that's going to get that overloaded cout function that we made for account, because that's going to be the data type returned here. So just to show you, mine looks like this at the moment. You can see I'm just printing out the accounts that I've made, and because I'm inserting at the head, the first one I created is going to be at the tail of the list, and the last account I created is going to be at the head of that list. So you can see that's what's happening here. Obviously, I'd suggest that you should do more with this list. You should try moving from the tail to the head. You should try inserting in a different order. So try inserting at the current and see how that goes. Just really get in there and play around and have a few more things to do with your list, but this should be enough to get you going and on your way. So that's the end of today's video. Hopefully you're in a good place to really get in there and play around with your linked list, and good luck with everything.